Hi, everyone. So as you might have noticed, my name is Rose, but everyone calls me Rosie, and I'm the newest professor. I'm starting in January. And I did my undergraduate in material science and engineering at the University of Connecticut, focusing on computer science, and my PhD in macromolecular science and engineering from the University of Michigan. And currently it is a little after 10 here because I am serving as a postdoc for the final couple months here in Lausanne, Switzerland at the Swiss Federal Institute of Technology. And in my spare time, I like to run, rock climb, and then bake a lot of things and hope the other two offset it. So, uh, yeah, so I'll talk to you a little bit today about what my group does. So we focus on an entire field called feature engineering. It's a field of research that's focused on the most efficient and effective ways to represent chemical entities for machine learning problems. So if you think about it, chemical entities, atoms, molecules, particles, whatever, they start as Cartesian coordinates. And simply looking at atoms, there's been this entire explosion of different ways to represent atoms. Read, if you will, for different sorts of machine learning, whether we want to learn things like vectorial quantities like dipole moments, or we want to learn energies, there's different ways to represent these chemical entities. Now, the way that you can kind of think about this is, say I have atoms or a group of atoms. Read. How do I numerically encode it into some sort of mathematical signal that we can then put into a machine learning model and most efficiently and effectively? So efficiently meaning quickest and most accurate, and effectively meaning that we're able to do the most with the data that we have. So specifically, my group is interested in how do we build from the atom scale up? How can we take a lot of the different successful practices that occur in atomic machine learning? So there's a lot of things occurring where we can have supervised machine learning models that take different sorts of representations and are able to build different models for different wide sorts of properties, but then take it up a couple scales, thinking about nanoparticles, macromolecules, and larger, what we would call building blocks, where there is really a dearth of these sorts of sophisticated and advanced ML models. So my group thinks about, okay, how can we expand these tools that are successful at the atomic scale to these sorts of larger entities, which can include things like different sorts of polymeric or globular proteins, different sorts of macromolecular things. And so the way that we do this is we simulate different sorts of interactions and macromolecular building blocks. And then we develop and apply machine learning methods to analyze and extract information from these simulations. How can we get all the information out of a simulation to make the future ones easier or faster? And then finally, we interpret these results to further either existing theory or develop design principles for new materials. And so if you want to learn more about what I do or want to talk potentially about joining my lab, this is my email address. And I somehow got the Twitter handle Lab of Science. So feel free to reach out to me and I would be happy to hear from you.